Picture an apple, fresh, firm, crimson skin, stretched tight over white flesh. Now watch it sit on your kitchen counter. Day 1, it's perfect. Day 2, a small brown spot appears near the stem. Day 3, the spot spreads. Day 7, the skin wrinkles. Day 14, it's rotting. Day 30, it's liquid. Now try this. Try to point to the exact moment, the precise instant, when the apple stopped being fresh and became rotten. You can't. Because there is no moment. There's only a sequence of states, each slightly different from the last. What you call time, that feeling of flow, of things moving forward, is just you comparing one state to another. The apple doesn't experience time. It simply exists in different configurations. And here's the disturbing part. All those configurations, from fresh to rotten, exist simultaneously in the structure of reality. They always have. They always will. Richard Feynman understood this. The man who could explain quantum mechanics to a child, who could crack safes at Los Alamos for fun, who played bongo drums in strip clubs while calculating the path of every photon in the universe, he looked at time and saw something nobody wanted to admit. Time doesn't flow. Time doesn't pass. Time doesn't exist as a thing moving forward. Time is just the measure of decay. And if that's true, then you, right now, listening to this, are not moving through time toward your future. Your birth, your first kiss, your last breath, they're all already there, frozen in the structure of space-time like insects in amber. You're not becoming, you already are. Every version of you, simultaneously. Let that sink in. Most people never question time. It feels obvious, undeniable. You wake up, breakfast happens, then lunch, then dinner, then sleep. The clock ticks forward, 60 seconds make a minute. 60 minutes make an hour. The sun rises in the east and sets in the west. Your body ages. Your friends age. Buildings crumble. Stars die. Everything flows in one direction. From past to future. From order to chaos. From life to death. Except, that's not what the mathematics says. Every fundamental equation in physics, Newton's laws, Maxwell's equations for electromagnetism, Einstein's field equations for gravity, even the Schrödinger equation that governs quantum mechanics, every single one of them works perfectly fine if you run time backwards. You can take t, the time variable, and replace it with negative t, and the math doesn't care. The laws of physics are time symmetric. Think about what that means. If you filmed a planet orbiting a star and played the footage in reverse, the equations would describe that backwards motion perfectly. If you filmed 2 billiard balls colliding and reversed it, physics would say, yes, that's allowed. The universe doesn't have a built-in arrow pointing from past to future. The equations don't prefer forward over backward. So why do we? Why can you remember eating breakfast this morning but not eating breakfast tomorrow morning? Why do eggs break when they fall but never spontaneously unbreak and leap back onto the counter? Why do we age forward instead of backward? Why does a cup of hot coffee cool down instead of a cup of cold coffee spontaneously heating up by stealing energy from the air? The answer most people give is, because that's just how time works. Time moves forward. Cause comes before effect. The past is fixed and the future is open. But Feynman didn't accept that answer, because the math, the deep, fundamental math, doesn't support it. If the laws of physics don't distinguish between forward and backward, then time's arrow, this feeling that we're all surfing a wave from past to future, must be coming from somewhere else. Not from time itself, from something else. Here's what Feynman realized. Time isn't a river carrying us from yesterday to tomorrow. Time is a map, a 4-dimensional map where every event that ever happened or ever will happen is already plotted. Your birth is a point on that map. Your death is another point on that map. And the thing we call the present moment, that sensation of now, is just your consciousness reading one slice of the map at a time. Imagine a movie. The entire film already exists on the disk or the server. Every frame, from opening credits to final scene, is sitting there, complete. When you watch it, you experience it, frame by frame, scene by scene, moving forward. But the movie itself isn't moving. It's static. It's finished. Your consciousness is just moving through it. That's what's happening with time. The universe. All of it. from the Big Bang 13.8 billion years ago to the heat death trillions upon trillions of years from now, already exists as a single, four-dimensional structure. Physicists call it the block universe. Einstein's relativity demands it. When Einstein showed that space and time aren't separate things but woven together into space-time, he also showed that past, present, and future aren't separate either. They're all equally real. All equally existent. All equally there. You think you're living in the present, moving toward the future, leaving the past behind. But that's an illusion, a trick of consciousness. The past isn't gone. The future isn't yet to come. They're both just elsewhere in space-time, as real as the room you're sitting in right now. This is hard to accept. Your brain rebels against it because it feels so deeply, viscerally like time is flowing, like you're moving forward, like the future is open and the past is closed. How can all of it exist simultaneously? How can your future already be written? The answer requires us to separate two things we usually confuse: time and change. We think time is the thing that makes change happen, but Feynman would flip that. Change is the thing that makes us perceive time. Take away change, freeze every particle in the universe, and time becomes meaningless. Not because time stopped, but because there's no longer any way to measure it. No decay, no motion, no difference between one moment and the next. Time doesn't create change. Change creates the illusion of time. And that change, that universal decay we observe, has a name: entropy. The tendency of ordered systems to become disordered. The reason ice melts but puddles don't spontaneously freeze. The reason your desk gets messier but never spontaneously organizes itself. The reason every star will eventually burn out and every galaxy will eventually go dark. Entropy only increases in one direction. And that direction, that one-way arrow from order to disorder, is what we call time. Time isn't a fundamental thing. It's an emergent property, a side effect, a bookkeeping device we invented to track the decay of the universe. If Feynman is right, if time is just decay, then everything changes. Free will becomes suspect. The future becomes inevitable. Death stops being something that will happen and becomes something that already exists, waiting in your personal future like a destination already marked on the map. You're not moving toward your death. You're already there. You've always been there. And the only reason you don't know it yet is because your consciousness hasn't read that part of the map. In the next part, we're going to explore exactly what this block universe looks like, how all of time can exist simultaneously, how the dinosaurs and your future grandchildren are equally real, equally present, just located in different regions of space-time. We're going to slice open reality and look at the architecture underneath. But first, sit with this thought. Try to catch the present moment. Try to grab hold of now. Where is it? When you think you found it, it's already gone. The present is infinitesimally thin, a mathematical point with no duration. You can't live in it because by the time you notice it, it's already past. So where are you? If the past is gone and the future hasn't arrived, and the present is too thin to occupy, where exactly do you exist? Imagine a loaf of bread, freshly baked, sitting on a cutting board. The entire loaf exists all at once, from the heel on one end to the heel on the other. Now pick up a knife and slice it. Each slice is a cross-section of the whole. Each slice looks complete, like it's the entire piece of bread. But it's not. It's just one thin layer of a larger structure. That's your life. The loaf is your timeline, from birth to death. Each slice is a single moment, a single now. When you experience Monday, you're experiencing one slice. When you experience Tuesday, that's the next slice. But the whole loaf already exists. Monday didn't disappear when Tuesday arrived. It's still there, just in a different part of the loaf. And Wednesday already exists too. You just haven't reached that slice yet. This is the block universe. And it's not a metaphor. It's not poetry. It's what Einstein's equations describe as the actual structure of reality. In 1905, Einstein published his special theory of relativity and destroyed the idea of universal time. Before Einstein, everyone assumed time was absolute, that there was one cosmic clock ticking away the same for everyone, everywhere. You could say right now, on Mars, and it would mean something precise. But Einstein showed that now is relative. It depends on how fast you're moving and where you are in a gravitational field. Two people moving at different speeds will disagree about what events are happening now, not because one of them is wrong, but because they're both right. There is no universal present moment. There is no cosmic now. What's present for you might be past for someone moving near the speed of light. What's future for you might be present for someone in a different reference frame. And if there's no universal now, if different observers slice up space-time differently, then past, present, and future can't be fundamentally different types of existence. They must all exist equally. The block universe solves this problem by saying, fine, all moments exist simultaneously, not in time, because time is part of the block, but in a timeless, eternal sense. The block just is. It doesn't change. It doesn't evolve. It doesn't become. It simply exists as a four-dimensional structure, and our consciousness moves through it like a spotlight moving across a stage. Hermann Weyl, one of Einstein's contemporaries, put it beautifully. He said, "The objective world simply is. It does not happen. Only to the gaze of my consciousness, crawling upward along the lifeline of my body, does a section of this world come to life as a fleeting image in space which continuously changes in time." Read that again. The world does not happen. It simply is. This means the dinosaurs still exist. Not in the past, because the past isn't a place where things used to be. The past is a region of space-time that exists just as solidly as the region you call now. 65 million years ago is a location in the block. It's there. The asteroid striking the Yucatan Peninsula is there. The dust cloud blocking out the sun is there. The last Tyrannosaurus drawing its final breath is there. Frozen, eternal, real. You could almost reach out and touch it if you could move through the fourth dimension the way you move through the three spatial dimensions. And your future exists too. Every choice you think you haven't made yet, already made. Already recorded in the structure of space-time. Your death, the moment your heart takes its last beat, your neurons fire their last signals, your consciousness winks out, that moment exists right now in your future light cone, as real and as solid as the moment you were born. You just haven't experienced it yet. But it's there. It's always been there. This is deeply, profoundly disturbing to most people, because it seems to eliminate free will. If your future already exists, if the choice you're going to make tomorrow is already encoded in the block, then how can you be said to choose freely? You're just reading a script that's already been written. Feynman was asked about this once, and his answer was, careful. The block universe doesn't mean determinism in the classical sense, because quantum mechanics adds fundamental randomness to the picture. The future exists, yes, but which future exists might not be determined until the wave function collapses. Or, in some interpretations, all possible futures exist in superposition. But even that doesn't save free will in the way people want. Because if the future is already there, already determined, or already branched, or already superposed, then you're not creating it. You're discovering it, you're experiencing it, but you're not authoring it. Think about what this means for identity. You think of yourself as a continuous being, the same person who was 5 years old, who is now your current age, who will be elderly someday. But in the block universe, you're not continuous. You're a stack of time slices, a four-dimensional object shaped like a worm, extending from your birth to your death. Each moment of you is a different cross-section of that worm. The you from yesterday is not the same time slice as the you from today. They're neighbors in the block, connected by physical continuity and memory, but they're distinct entities. You at age 5 and you at age 50 are as different as two separate people, except they happen to be part of the same four-dimensional structure. And all of those yous exist simultaneously. The child you were still exists, not in memory, not in photographs, actually exists in that region of space-time we label as 20 or 30 or 40 years ago. That child is still there, still experiencing those moments, still feeling those feelings. You didn't stop being that child. You just moved to a different part of the block. Some physicists find this comforting. Your loved ones who have died, they still exist in their region of space-time. They're still there, living those moments, experiencing that joy or that pain or that love. Death doesn't erase them from existence. It just means you've moved to a part of the block where your timeline and theirs no longer overlap. Other physicists find it horrifying. Every moment of suffering you've ever experienced still exists, still happening. The worst day of your life is not over. It's frozen in the block, eternal, endlessly recurring in the sense that it's always there whenever you examine that region of space-time. Both views are correct. But here's the question Feynman would ask. If all of time already exists, if the block is static and eternal, then why do we perceive motion at all? Why does it feel like time is flowing? The answer brings us back to entropy. Imagine you're watching a movie, but you're watching it one frame at a time, with long pauses between frames. Each frame is a complete image, a snapshot of reality at one instant. The frames don't move, they're static images. But when you play them in sequence, you perceive motion, you perceive change, you perceive a story unfolding. Your consciousness does the same thing with the time slices of the block universe. Each slice is static, but your consciousness, which is itself a process distributed across many time slices, experiences them in sequence, and that sequence is ordered by entropy. Your brain records memories in states of higher entropy. The version of you 5 seconds from now has slightly higher entropy than the version of you now. More disorder, more decay, more thermodynamic arrow pointing forward. And because memory only works in one direction, from lower entropy to higher entropy, you perceive time as flowing in that direction too. If entropy somehow reversed, if the universe spontaneously started becoming more ordered instead of more disordered, your perception of time would reverse too. You'd remember the future and be ignorant of the past. Cause and effect would flip. But that never happens on large scales. Entropy always increases. The second law of thermodynamics is the most ironclad law in all of physics. And that one-way increase in disorder is what creates the illusion of time flowing forward. Feynman used to illustrate this with a thought experiment. Imagine a box divided in half by a partition. On one side, you have 100 gas molecules. On the other side, nothing, a vacuum. Now you remove the partition. What happens? The gas spreads out. The molecules bounce around randomly until they fill the entire box uniformly. That's entropy increasing. Order, all molecules on one side, becoming disorder, molecules spread everywhere. Now ask yourself, will you ever see all those molecules spontaneously gather back on one side of the box? Technically, it's possible. The laws of physics allow it. Each molecule is just bouncing around randomly, and there's a tiny, tiny probability that they'll all randomly happen to be on one side at the same instant. But the probability is so astronomically small that you could watch the box for billions of times the age of the universe and never see it happen. That's why time appears to flow forward. Not because the laws of physics demand it, but because there are vastly more ways for things to be disordered than ordered. And random motion naturally explores the more probable states. A broken cup has more possible configurations than an intact cup. A dead organism has more possible molecular arrangements than a living one. The heat death of the universe has more possible states than the hot, dense, ordered state of the Big Bang. The universe isn't being pushed toward disorder by some force. It's just statistically exploring all available states, and the overwhelming majority of those states are disordered. Time is just the direction in which entropy increases. And here's the truly strange implication. If you could somehow reverse entropy, if you could take a broken cup and guide all its molecules back into the exact configuration they had before it shattered, you wouldn't just be reversing an event. You'd be reversing time itself. The cup wouldn't remember being broken. From the cup's perspective, it would simply transition from one state to another, and the unbreaking would feel like normal time moving forward. Time doesn't flow. Entropy flows. And we call that flow time. In the next part, we're going to dig deeper into entropy. We're going to explore why disorder increases, why the universe started in such a low entropy state, and what it means that we exist in this narrow window, this brief cosmic moment when entropy is high enough for complexity to exist, but low enough for change to still happen. We're going to watch the universe die, and we're going to understand why that death is the only thing that makes our lives possible. Drop a wine glass on a tile floor. It shatters. Hundreds of pieces scatter across the ground. Red liquid spreads in a puddle. Now, reverse it. Watch the shards leap up from the floor, reassemble themselves perfectly, the wine flowing backwards into the reformed glass, which lands gently in your hand. You've never seen this happen. You never will. But why not? Every individual molecule involved in that shattering, every atom of silicon dioxide in the glass, every water molecule in the wine, every air molecule pushed aside by the falling pieces, every single one of them obeys laws of physics that work perfectly well in reverse. The equations don't care. So why does the universe care? Why does the glass break but never unbreak? This is the arrow of time. And it all comes down to one word: entropy. The measure of disorder in a system. The measure of how many ways you can arrange the components of something while still having it look the same at the macroscopic level. An intact wine glass has low entropy. There's basically one way to arrange the atoms so that you have a functional wine glass. Maybe a few thousand ways if you account for tiny variations in crystal structure. But that's nothing. A shattered wine glass has high entropy. There are trillions upon trillions upon trillions of ways to arrange those shards on the floor. Each shard could be rotated slightly, positioned differently. The puddle could spread in countless different patterns. The number of possible configurations is staggeringly, incomprehensibly large. And that difference, that's everything. The second law of thermodynamics states that in any isolated system, entropy always increases or stays the same, never decreases. This is not a fundamental law in the same way that conservation of energy is fundamental. It's a statistical law, a probabilistic law. It emerges from the sheer numbers involved. When you drop the glass, the atoms don't want to increase entropy. They don't try to become more disordered. They just bounce around randomly according to the laws of physics. But there are so many more high entropy arrangements than low entropy arrangements that random motion almost always leads from order to disorder. It's not impossible for the glass to spontaneously reassemble. It's just so improbable that it will never happen in the lifetime of the universe. Never. Feynman had a way of making this visceral. He'd say, imagine you have a deck of cards, perfectly ordered, ace through king of spades, then hearts, then diamonds, then clubs. That's low entropy. One specific arrangement out of how many possible arrangements? 52 factorial. That's 52 times 51 times 50 times 49, all the way down to 1. The number is 8 with 67 zeros after it. More than the number of atoms in the observable universe. Now, shuffle the deck once. What are the odds you'll get back to that perfect order? Effectively 0. Shuffle it a billion times. Still effectively 0. The ordered state is one arrangement out of an unimaginable ocean of disordered states. And every time you shuffle, you're almost certainly moving toward a more disordered state. Not because disorder is favored by the laws of physics, but because disorder is almost all there is. This is why time has an arrow. Not because the past is fundamentally different from the future, but because the past in our universe happens to be a low entropy state. And the future is the direction in which entropy increases. Think about a cup of hot coffee sitting on a table. The coffee is hot, the air around it is cool. That's a low entropy state. The energy is concentrated, organized, separated into hot region and cool region. Over time, the heat flows from the coffee into the air. The coffee cools down, the air warms up slightly. Eventually, they reach thermal equilibrium. Same temperature everywhere. That's higher entropy. The energy is spread out, disorganized, homogeneous, and it never goes back. The coffee never spontaneously gets hotter by stealing energy back from the air. Why? Because there are vastly more ways for the energy to be spread out than concentrated. The molecules of hot coffee and cool air are jiggling randomly, and random jiggling naturally explores the space of all possible energy distributions. And the overwhelming majority of those distributions have the energy spread out evenly. Every irreversible process you've ever witnessed, every broken egg, every melted ice cube, every mixed paint color that can never be unmixed, every aging face, every cooling star, every dying organism, all of it is entropy increase. All of it is the universe exploring its vast space of possible configurations and finding that almost all of them are disordered. And this relentless march from order to disorder is what you experience as time passing. Time doesn't make things decay. Decay is what we call time. But here's the mystery. The equations work both ways. So why did the universe start in a low entropy state? The Big Bang, 13.8 billion years ago, was the lowest entropy state the universe has ever been in. All the matter and energy in existence compressed into an infinitesimally small point. Incredibly hot, incredibly dense, but also incredibly ordered. Why? If entropy always increases, how do we get a low entropy beginning? This is one of the deepest unsolved problems in physics. Feynman knew it, Einstein knew it, every cosmologist knows it. The arrow of time points away from the Big Bang because the Big Bang was special, unusual, improbable. It was a state of extraordinarily low entropy, and everything since then has been the universe relaxing into more probable, higher entropy states. But why was the Big Bang low entropy to begin with? One possibility, it wasn't. Maybe the Big Bang was actually a high entropy state for the conditions at that time. Maybe our intuitions about order and disorder break down in the extreme physics of the early universe. Maybe what looks like low entropy to us was actually the maximum entropy possible given the constraints of quantum gravity. Another possibility, the Big Bang wasn't the beginning. Maybe it was a transition from a previous state. Maybe the universe is cyclical, expanding and contracting, and entropy resets somehow during the bounce. Though this has problems. Where does the information go? How does entropy decrease? A third possibility, the one Feynman might have liked, is that we exist in a universe with a low entropy past simply because we have to. Observers like us, complex information processing organisms, can only exist in a universe with a strong entropy gradient. We can only exist in the middle of the decay process, not at equilibrium. Life is a temporary decrease in local entropy, sustained by a much larger increase in entropy elsewhere. When you organize your thoughts, when you build a house, when you grow from a single cell into a human being, you're decreasing entropy in your immediate vicinity. But you're paying for it. You're burning fuel, generating heat, increasing the entropy of your environment by more than you're decreasing your own entropy. Life is an eddy in the stream of entropy increase, a brief local reversal powered by the global flow toward disorder. And when that flow stops, when the universe reaches maximum entropy, life becomes impossible, thought becomes impossible, change becomes impossible. Time stops. Think about what entropy really means at a deep level. It's a measure of information, of how much you don't know about the exact microstate of a system. A low entropy system is predictable, ordered. You can describe it with relatively few parameters. A high entropy system is unpredictable, disordered. You need vastly more information to describe every detail. And here's the connection to time. The reason you remember the past but not the future is because the past is low entropy. There are relatively few ways the universe could have been 5 seconds ago that would lead to the present state. But there are many, many ways the universe could evolve over the next 5 seconds. Your memories are low entropy records of past states. They work because the past is more ordered than the present. If entropy were decreasing instead of increasing, you'd remember the future and be surprised by the past. Feynman loved to play with this idea. He'd ask students, if you see a puddle on the floor and footprints leading away from it, you naturally conclude someone tracked water across the room. You're using the asymmetry of time. You're assuming the puddle came before the footprints, not after. But what if entropy were reversed? What if the universe were contracting back toward a low entropy state instead of expanding toward a high entropy state? Then the footprints would come before the puddle. Someone would walk backward across the room, somehow pulling water out of the floor with their shoes, leaving a puddle behind. Absurd, right? Only if you privilege one direction of time over the other. The physics allows both. It's only the entropy gradient that makes one direction seem normal and the other direction seem insane. And that means something profound. The flow of time, the sensation of moving from past to future, of memories forming, of cause preceding effect, is not built into the fabric of reality. It's an emergent property of living in a universe that happens to have a low entropy boundary condition at one end. If you could somehow flip that boundary condition, if the Big Bang were high entropy and the far future were low entropy, the subjective experience of time would reverse. You'd still feel like you were moving from past to future. But future would be the direction of decreasing entropy, toward order, toward the big crunch. Time doesn't flow. We flow through a static landscape of entropy gradients, and we call that flow time. There's a haunting implication here. Everything you've ever lost, every friendship that faded, every love that ended, every pet that died, every version of yourself that you grew out of and left behind, all of it is entropy increase. The ordered state, the The specific, low probability configuration of atoms that made up that friendship, that love, that pet, that younger you dissolved into the chaos of higher entropy states. And it's irreversible. Not because the laws of physics forbid reversal, but because the statistical weight of disorder is so overwhelming that reversal will never happen. The glass will never unbreak. The dead will never come back to life. The past will never return. Not because time flows forward, but because disorder drowns everything. In the next part, we're going to explore something even stranger. Feynman discovered that at the quantum level, particles can move backward in time. An electron traveling from future to past looks exactly like a positron, antimatter, traveling from past to future. This raises a disturbing question. Is time travel happening constantly at the smallest scales of reality? And if so, what does that mean for the arrow of time we experience at our scale? We're about to find out. 1940. A young Richard Feynman is sitting in a graduate student office at Princeton, talking with his advisor, John Wheeler. They're trying to solve a problem with quantum electrodynamics, the theory of how light and matter interact. The equations keep spitting out infinities, nonsense answers. The math is broken. And then Wheeler says something strange. What if an electron could travel backward in time? Pause. Feynman thinks Wheeler is joking, but Wheeler is serious. He explains, what if, when we see a positron, the antimatter counterpart of an electron, we're not actually seeing a different particle? What if we're seeing the same electron, moving backward through time? Feynman stares at him, and then slowly the mathematics starts to click into place. An electron has negative charge. It moves forward through time from past to future. A positron has positive charge. It moves forward through time from past to future. But mathematically, a positron moving forward in time is identical to an electron moving backward in time. Identical, not similar, not approximately the same, exactly the same. If you film an electron going from point A to point B and play the footage backward, it looks like a positron going from point B to point A. The charge appears to flip, the direction appears to flip, but the underlying physics is the same. This became one of Feynman's most famous insights. In his diagrams, the Feynman diagrams that every physics student learns, time runs upward on the page. An electron moving upward is an electron moving forward in time, but a positron moving upward is mathematically equivalent to an electron moving downward, backward in time. When an electron and positron collide and annihilate into pure energy, what's really happening? From one perspective, two particles meet and destroy each other. From another perspective, a single electron reaches the moment of annihilation, reverses its direction in time, and heads back the way it came. Same event, different interpretation, both correct. Wheeler took this idea even further. He called Feynman on the phone one day. Feynman tells this story in his lectures and said, "I know why all electrons have the same charge and the same mass." Feynman asked why. Wheeler said, "Because they're all the same electron." Think about it. One electron, weaving back and forth through time, creating an incredibly complex path through space-time. Sometimes it's moving forward. We see it as an electron. Sometimes it's moving backward. We see it as a positron. The entire universe, all the electrons and positrons that have ever existed, could be a single particle tracing a tangled web through the fourth dimension. Feynman loved the idea, but he saw the problem immediately. If that were true, there should be equal numbers of electrons and positrons in the universe. Every forward strand would need a backward strand. But there aren't. Electrons vastly outnumber positrons in our universe. So the idea doesn't work, not as a literal explanation for why all electrons are identical, but it works as something else, as a way of thinking about time symmetry at the quantum level. At the scale of individual particles, time reversal is built into the equations. The Dirac equation, the relativistic quantum equation for electrons, treats forward and backward time motion on equal footing. CPT symmetry, a fundamental theorem in quantum field theory, says that the laws of physics remain unchanged if you simultaneously reverse charge, parity, and time. Reverse all three and you get the same physics, which means at the deepest level, nature doesn't distinguish between an electron moving forward and a positron moving backward. There are two ways of describing the same phenomenon. Time symmetry isn't broken at the quantum level. It's only broken at the macroscopic level, where entropy takes over. This raises a disturbing question. If particles can move backward in time at the quantum scale, why can't we? Why can't macroscopic objects, people, planets, galaxies travel into their own past? The answer again is entropy. When a single electron reverses its time direction, it doesn't violate the second law of thermodynamics. One particle has essentially zero entropy. But when a human tries to reverse time direction, they'd have to carry their entire entropy history with them. They'd have to unscramble eggs, unburn fuel, reassemble every broken molecule. Statistically impossible. Time travel at the quantum level happens constantly. Pair production. When a photon creates an electron-positron pair, can be viewed as a photon causing an electron to briefly reverse its time direction, creating a closed loop in space-time. Virtual particles, the quantum fluctuations that fill empty space, can be interpreted as particles briefly traveling backward in time before returning to forward motion. But none of this violates causality at the observable level. The information doesn't propagate backward. The entropy still increases globally. The arrow of time remains intact for everything we can measure directly. Feynman used this time reversal symmetry to reformulate quantum mechanics. His path integral formulation says, to calculate the probability of a particle getting from point A to point B, you sum over all possible paths connecting them, not just the obvious paths, all paths, including paths where the particle briefly goes backward in time, including paths where it zigzags wildly through space, including paths that violate every classical intuition you have about how things move. And miraculously, when you sum all these crazy paths together, weighting each one by its quantum amplitude, you get the correct answer. You get predictions that match experiments to 15 decimal places. Reality doesn't choose one path. It explores all paths simultaneously, including the ones that involve time reversal. There's something philosophically profound happening here. At the fundamental level, time symmetry is preserved. An electron moving forward is equivalent to a positron moving backward. The equations don't care which direction is which. The laws of physics are time symmetric. But at the macroscopic level, the level of broken glasses and aging bodies and dying stars, time symmetry is broken. Entropy increases in one direction and one direction only. We remember the past, not the future. Causes precede effects. The arrow points forward. So which is real? The time-symmetric quantum level or the time-asymmetric thermodynamic level? Feynman would say both. They're describing different aspects of the same reality. At the scale of individual particles, time is reversible and symmetric. At the scale of large collections of particles, statistical mechanics takes over, and entropy creates an arrow. Time doesn't fundamentally exist at the quantum level. There's no flow, no direction, just patterns of correlation between events. But when you zoom out, when you look at systems with 10 to the 23rd particles, patterns emerge, entropy emerges, and with entropy comes the illusion of time flowing. But here's where it gets even stranger. Quantum mechanics introduces something that classical physics doesn't have: uncertainty, probability, indeterminacy, and this adds a new wrinkle to the block universe picture. In classical physics, if you know the exact state of every particle at one moment, you can in principle calculate the exact state at any other moment, past or future. The block universe is deterministic. Your future is already determined, already existing, already inevitable. But quantum mechanics says, no, you cannot know the exact state. There's fundamental uncertainty built into reality. Until you measure something, it exists in a superposition of multiple states. The wave function describes probabilities, not certainties. So does this mean the future isn't determined? Does this mean the block universe picture is wrong? Not exactly. It means the block might be probabilistic rather than deterministic. Instead of one fixed future, there's a probability distribution over many possible futures. And which one you experience might not be determined until the moment you experience it. Or, if you believe the many worlds interpretation, all possible futures exist, the block branches. Every quantum measurement creates a split, and all branches are equally real. You experience one branch, but other versions of you experience other branches. In that view, the block universe becomes a branching tree, or better, a dense thicket of timelines, all coexisting, all equally real, with your consciousness following one thread through the tangle. Feynman was agnostic about interpretations of quantum mechanics. He famously said, "I think I can safely say that nobody understands quantum mechanics." He knew the math worked. He knew the predictions were accurate. But he wasn't sure anyone, including himself, truly understood what the math meant. Does the electron really go backward in time when it becomes a positron? Or is that just a useful mathematical fiction, a way of making the calculations work that doesn't correspond to physical reality? Feynman would say, the question is meaningless. Physics tells us how to calculate what we'll observe. It doesn't tell us what's really happening behind the observations. All we have are the equations and the experiments. The rest is interpretation. But even if time reversal at the quantum level is just a mathematical trick, it's a trick that works. It's a trick that reveals something about the deep structure of physical law. Time symmetry is fundamental. Time asymmetry is emergent. The arrow is real, but it's not woven into the basic fabric. It's a pattern that appears when you zoom out. And this brings us to a final, unsettling realization. If time is just entropy increase, and entropy increase is just a statistical tendency, not a law, then time itself is not fundamental. Time is approximate, emergent, a useful bookkeeping device that works at large scales but breaks down at small scales. At the Planck scale, 10 to the minus 43 seconds, the smallest meaningful unit of time, the concept of time might not even make sense. Space-time itself becomes quantum foam, fluctuating wildly, with no clear distinction between past and future, cause and effect, before and after. Time might not exist at the foundation of reality. It might only emerge when you coarse grain over vast numbers of quantum events, when you blur your vision and look at the average behavior instead of the exact details. Which means the sensation you have right now, the feeling of existing in the present moment, of time flowing forward, of having a past and moving toward a future, is not a perception of fundamental reality. It's an illusion created by your macroscopic existence in a universe with a low entropy past. You are not moving through time. Time is not passing. You are a static pattern in the block universe, and the pattern happens to include records, memories, that give you the illusion of having moved from past to present. Consciousness doesn't flow through time. Consciousness is time. The subjective experience of duration, of before and after, of change. That's entropy increase viewed from the inside. In the final part, we're going to follow this logic to its ultimate conclusion. If time is just entropy increase, what happens when entropy reaches its maximum? When the universe expands and cools until every star has burned out, every black hole has evaporated, and every particle is spread so thin that nothing ever interacts with anything else again? What happens when decay stops? We're going to watch time die and understand why we should be grateful. Grateful that we exist in this brief window when decay is still possible, when change is still possible, when life is still possible. The universe is dying, and that's the only reason we're alive. 100 trillion years from now, the last star will flicker and die. Not 100 trillion years from the Big Bang, 100 trillion years from today, from the moment you're listening to this. The universe is 13.8 billion years old now. It's barely begun. The Stelliferous era, the age of stars, will continue for thousands of times longer than the universe has already existed. But it will end. Every star in every galaxy will exhaust its fuel. The massive ones will explode as supernovae or collapse into black holes. The medium ones will swell into red giants and then fade into white dwarfs, Earth-sized embers radiating away their remaining heat. The small ones will burn slowly for trillions of years, but even they will eventually sputter out. And then, darkness? The universe will be filled with dead stars, black holes, planets frozen at near absolute zero, dust, nothing burning, nothing shining, nothing warm. But the universe won't be done dying yet. 1 Google years from now, that's 10 to the power of 100, a 1 followed by 100 zeros. Even the black holes will be gone. Hawking radiation will cause them to evaporate, slowly releasing their mass back into space as particles and photons. The largest supermassive black holes, billions of times heavier than the sun, will take the longest, but they too will eventually radiate away into nothingness. And what remains? A vast, cold, dark expanse. Individual particles spread so far apart that they will never interact again. Photons stretched by cosmic expansion until their wavelengths span light years. A universe in perfect thermodynamic equilibrium, maximum entropy. Heat death. At maximum entropy, nothing happens. There are no gradients, no differences in temperature, no differences in energy density, no differences in anything. Every region of space is identical to every other region, and without differences, there can be no change, no flow of energy, no work, no complexity, no time. Not because time stops, but because the concept becomes meaningless. Time is the measure of change. If nothing changes, there's nothing to measure. The universe reaches a state where every moment is identical to every other moment. Past, present, and future become indistinguishable. The universe becomes a static, timeless void, and it will remain that way forever. This is the ultimate fate predicted by thermodynamics. Entropy increases until it can't increase anymore, and then stasis, eternal, unchanging, dead equilibrium. The heat death of the universe. Feynman understood this. He knew that the arrow of time we experience, the flow from past to future, from birth to death, from order to disorder, is temporary. A brief phase in cosmic history when the universe happens to be far from equilibrium. We exist in a Goldilocks moment, early enough that stars still burn, late enough that heavy elements forged in supernovae have created planets and chemistry and life. We exist in the narrow window, cosmologically speaking, when entropy is high enough for complexity, but low enough for change. Before us, the Big Bang. Infinitely dense, infinitely hot, perfectly ordered in some sense we don't fully understand. Low entropy. After us, heat death, infinitely diffuse, infinitely cold, perfectly disordered, maximum entropy. And in between, this, stars and planets, oceans and atmospheres, DNA and neurons, consciousness, love, music, mathematics. All of it existing because we're in the middle of the decay process. Life is only possible in disequilibrium. You are a dissipative structure, a temporary pattern of low entropy maintained by a constant flow of energy and matter through your body. You eat food, low entropy, chemical energy. You metabolize it. You radiate heat, high entropy, thermal energy. You increase the entropy of the universe more than you decrease your own entropy. You stay alive by accelerating the heat death of the universe. Every thought you think, every motion you make, every breath you take, all of it is paid for by increasing disorder elsewhere. You are a local reversal of entropy, purchased at the cost of global entropy increase. You are fighting the second law and losing in exactly the way that allows you to temporarily win. And when your body can no longer maintain that energy flow, when your metabolism shuts down, when your neurons stop firing, when your heart stops beating, entropy wins. Your structure dissolves. The pattern that was you dissipates into heat and simple molecules. You return to equilibrium. Death is what happens when you can no longer fight entropy, when the cost of maintaining order becomes too high, when the gradients that sustain you flatten out. Death is personal heat death. But here's the strange comfort in Feynman's view. You don't disappear from the block universe when you die. Your timeline doesn't end. It just stops extending into higher time coordinates. The four-dimensional shape, that is you, stretching from your birth to your death, remains embedded in space-time forever. You are eternal, just not in the way people usually want to be eternal. And the universe's heat death? That too is eternal. Once maximum entropy is reached, there's no coming back, no big crunch to restart the cycle. Current evidence suggests the universe will expand forever, driven by dark energy, getting colder and emptier and deader for all of eternity. Unless we're wrong about something fundamental. Unless there's new physics we haven't discovered. Unless the universe is cyclical in ways we don't understand. Unless quantum fluctuations can somehow birth new big bangs from the void of heat death. These are possibilities, speculations. But the mathematics of thermodynamics is brutally clear. In an isolated system, entropy always increases. And the universe, by definition, is the ultimate isolated system. Pause. Feynman used to point out something darkly funny about this. The second law of thermodynamics, entropy always increases, is the only law in physics that distinguishes past from future. It's the only law that's time asymmetric. Every other law works the same backward and forward. So the arrow of time, the flow we experience, the difference between cause and effect, all of it rests on one statistical tendency, on the fact that there are more disordered states than ordered states. That's it. That's all time is. A statistical artifact of living in a universe that started in a low entropy state and is relaxing toward maximum entropy. Remove that, equilibrate the universe, and time vanishes. There's something both terrifying and liberating about this view. Terrifying because it means everything ends. Not just your life, not just humanity, not just Earth or the sun or the galaxy. Everything. All structure, all complexity, all change. The universe will become a featureless void and remain that way forever. But liberating because it means we're here now, against staggering odds. In the brief cosmic eye blink, when stars shine and planets orbit and molecules assemble into living things that can think and feel and wonder, the universe is dying. Has been dying since the Big Bang. Entropy has been increasing for 13.8 billion years, and it will continue increasing for trillions upon trillions of years more. But right now, we exist in the sweet spot, the moment of maximum complexity, when entropy is high enough to have created rich chemistry and low enough to still allow change. We are the universe becoming conscious of itself during its decay phase. We are patterns of information processing, temporarily carved out of the energy flow from low entropy to high entropy. We are eddies in the stream of time, existing only because the stream is flowing. And when the stream stops flowing, when equilibrium is reached, we won't exist anymore. Not because we'll die, but because consciousness requires disequilibrium. Thought requires energy gradients. Memory requires the arrow of time. At heat death, there are no gradients, no arrow, no memory, no thought, no consciousness. Just eternal, unchanging, timeless void. Feynman was asked once how he felt about this, about the heat death, about the ultimate meaninglessness of everything if the universe ends in cold, dark equilibrium. He said, "It doesn't bother me. I find it interesting." Because here's what Feynman understood. Meaning isn't something the universe gives you. It's something you create. During your brief existence, in your tiny corner of space-time, meaning emerges from complexity, from consciousness, from the ability to observe and think and feel. And that ability only exists because we're in the decay phase, because entropy is increasing, because time, as we experience it, is flowing. The fact that it all ends doesn't make it meaningless. It makes it precious, finite, irreplaceable. You have one timeline in the block universe, one four-dimensional path from birth to death, and every moment of that path exists eternally, frozen in space-time, as real as any other moment in cosmic history. The dinosaurs still exist in their region of space-time. The first stars still exist in theirs, and you, right now, in this moment, exist in yours, eternally, unchangingly, forever embedded in the structure of reality. So what do we do with this knowledge? How do we live knowing that time doesn't flow, that the future already exists, that the universe is dying and we're just temporary patterns in its decay? Feynman's answer: we pay attention. We look closely at the world. We marvel at the complexity that entropy has temporarily created. We use our brief window of consciousness to understand as much as we can. Because even if the universe is deterministic, even if every choice you make is already encoded in the block, you still experience making those choices. You still feel the weight of decisions. You still suffer and love and dream and hope. The experience is real. Even if it's predetermined, even if it's just patterns of neurons firing in accordance with physical law, the suffering of a conscious being is real suffering. The joy is real joy. The love is real love. Nothing about the block universe or entropy or the heat death changes that. We are the universe looking at itself for a brief moment in a tiny region of space-time before the long silence. And maybe, that's enough. Maybe the meaning of existence isn't to last forever. Maybe it's to exist at all, to be a pattern complex enough to experience being a pattern, to be the universe achieving self-awareness, even if only temporarily. Every thought you have, every connection you make, every moment of understanding, these are the universe knowing itself. And when you die, when your pattern dissolves, that knowledge doesn't disappear from the block. It remains, eternally embedded in your timeline, part of the permanent structure of space-time. You were here. You existed. You contributed to the universe's brief experiment with consciousness. That matters, even if it ends. So here's your final question, the one Feynman would want you to think about. If time doesn't flow, if it's just decay, just entropy increase, just a statistical tendency with no fundamental significance, then what are you going to do with your slice of the block universe? With the four-dimensional shape that is your life? You can't change it. From the outside perspective, it's already complete, already determined, already sitting in space-time like a sculpture in a museum. But from the inside perspective, from your conscious experience moving through the slices, you get to discover what shape your life has. You get to experience the choices, the consequences, the joy and suffering and meaning. The universe is dying. Time is an illusion. Free will might be an illusion. Consciousness might be an illusion. But the experience of being alive right now, in this moment, that's real. And that experience is built on decay, on entropy increase, on the fact that the universe started in a low entropy state and is relaxing toward maximum disorder. We exist because things break, because energy flows downhill, because the universe is far from equilibrium and stumbling toward heat death. We are children of entropy, temporary patterns in the cosmic decay, here for an eye blink, gone for eternity. And somehow, impossibly, improbably, beautifully, aware of it all. Feynman spent his life trying to understand the universe, not to find meaning, not to discover purpose, just to see it clearly, to strip away the illusions and look at the mathematics underneath. And what he found was this: time doesn't exist. Not really, not fundamentally. There's just the block, the four-dimensional structure, the eternal present containing all past and future. And entropy, the statistical tendency toward disorder, the only arrow in the timeless equations. That's it. That's all time is. The measure of things breaking. And you are one of the things that's breaking. Slowly, inevitably, moving from low entropy to high entropy, from order to disorder, from pattern to noise. You are time. And time is you. And when you stop breaking, when you reach your personal heat death, time will stop for you, not because you'll be dead, but because death is what we call it when the entropy gradient flattens, when change becomes impossible, when the arrow points nowhere. So break beautifully, decay gracefully, use your brief window of disequilibrium to create something, learn something, love something. Because in 100 trillion years, the stars will go out, and in 10 to the 100 years, the black holes will evaporate. And in some unimaginable time after that, the universe will reach maximum entropy. And time, this illusion we've lived our entire lives inside, will cease to exist. Not because it ended, but because it was never really there to begin with. Long pause. This has been E-Man Frequency. Thank you for watching. Now go live. While decay is still possible, while time, this beautiful illusion, still exists,